Okay, we're here with part two of polar form of conic sections, and just a follow up to the last video, example one, that in each of those previous graphs in the last video, they were parabolas, and that's going to be the case when E, our eccentricity, equals 1. So our directrix lines are either going to be x equals positive or negative d, or y equals positive or negative d, again, depending on which way the parabola is opening, and our focal diameter is going to be 2 times that value of d. All right, so example 2, we're going to examine the graphs of each of the following for different values of d, but we're going to also look at values of e where e is between 0 and 1 and where e is greater than 1. So this time we're not going to have e equals 1. We're going to have it either be between 0 and 1 or greater than 1. So let's start with our first one. And here I'm going to set the value of e to be between 0 and 1. It could be 0.5, it could be 0.4, and then we'll adjust the values of d. So here's our graph. We have 0.4 times 1 over 1 plus 0.4 cosine theta. We take a look at changing the value of d, and now growing the other way. We can also make e something like 0.7. So here we have an ellipse, and don't want to get that far. If e is really close to 0, shrink our. There we go. So, but when e is between 0 and 1, we have a wide ellipse. For values of e bigger than 1, so let's look at e as 1.9, notice we have a hyperbola that's opening left and right. And as we increase the value of d, notice the distance between the branches are getting greater. And even if we make d more and more negative, it's just shifting over to the negative side on the x-axis. So if d is bigger than 1, we have a hyperbola that is going to open left and right. Now let's take a look at 1 minus e cosine theta in our denominator. So we'll start with value of e between 0 and 1. We'll pick 0.6. So here's our equation, or our graph. So notice again we have an ellipse, and if I make it between 0 and 1 for e, it's going to make it the ellipse wide. So when e is between 0 and 1, our graph is going to be a wide ellipse. For values of e that are bigger than 1, we again get a hyperbola that opens left or right. So here's where d is negative, and here's where d is positive. So not only is it going to either increase or decrease the distance between the branches, between the two vertices, it's also going to shift it left or right. So it's a hyperbola opening left and right. Next up, 1 plus e sine theta. We're going to take a look when e is between 0 and 1. So we'll make this between 0 and 1. We'll make it 0.8. And we get, appears to be an ellipse. And this ellipse is going to be tall versus a wide ellipse. So notice this one's opening up and down. Again, we have the sine of theta here, which we typically associate sine with the y-axis. So for values of e between 0 and 1, it's going to be a tall ellipse. For values of e greater than 1, well, hopefully you're thinking, I'm going to hide this for a sec, and here's a value that is greater than 1. And hopefully your suspicions are confirmed that it is in fact a hyperbola that opens up or down. So just like we had the hyperbola left and right for cosine, we have the hyperbola up and down for sine. So this time we have for values of e greater than 1, we have a hyperbola which is opening up and down. All right, looking at the graphs for 1 minus e sine theta. So looking at the graphs of 1 minus e sine theta. We're going to start with a value of e between 0 and 1. And let's see what that looks like. Well, changing the value of d, we get yet another ellipse that is going to be a tall ellipse. So for values of e between 0 and 1, we have a tall ellipse. And for values of e bigger than 1, you probably have a pretty good idea. And let's see if those are confirmed. And yes, we do get hyperbolas that open up and down. So hyperbola opening up and down. So in the previous examples, the graphs for which e were between 0 and 1 were ellipses with a major axis length, the distance between the vertices, as 2 times e times d over 1 minus e squared. A minor axis length, the distance between the covertices, is 2 times e times d over the square root of 1 minus e squared. For graphs bigger than 1, we had a hyperbola where the transverse axis, the distance between the vertices, is 2 times e times d over e squared minus 1. And the conjugate axis length, the distance between the covertices, 2 times e times d over the square root of e squared minus 1. All right, so that about does it for this video. I will see you next time.